Good morning. I'm Steve Wall, and this is Magellan at Venus. We have one exciting event to report, although not as exciting because it's happened to us before. And today we'll talk about image interpretation. Instead of concentrating on what we're seeing on Venus, today we're going to get someone to tell us more about how. In other words, how you tell what's what on these radar images. So we'll talk about that in a second. First of all, let's review where we are on the planet. If we were mapping the Earth, we would have started at Los Angeles in our little scenario here, and we would be today over the continent of Australia, headed out over the Pacific, still aiming for getting back around to what would be Los Angeles by May 15th. And as we've said before, starting on May 16th, we'll begin with Cycle 2 coverage. Cycle 2, the second time around, we'll concentrate mostly on filling the gaps that we've had as we've had the various geometric occultations, which we've told you about, filling the gaps from some of the problems that we've had. But we'll also begin to look at how are we going to conduct Cycle 3. We'll begin to do some little tests to tell us what different kinds of observations will tell us the most about how this planet functions. Cycle 3 promises to be a fairly exciting time. We'll concentrate on getting some gravity data. We watch the Magellan spacecraft without taking radar data, but instead pointing back toward Earth so that we can measure very carefully these little Doppler shifts in the frequency to tell us exactly how the spacecraft is reacting to gravity local anomalies. And I guess I shouldn't use the word anomaly because we use that to say something's wrong with the spacecraft, but where there's a gravity concentration, a concentration of mass within the planet, what happens is that the spacecraft orbit reacts to that, and we can tell the difference between a place where there is a concentration of mass and a place where we have the normal density of the planet. Today is Wednesday. On Monday evening, the spacecraft experienced another of what we've been calling walkabouts, where the attitude control computer goes away for some reason that we don't quite understand. We have protected ourselves well enough against these attitude control walkabouts that they don't affect our mapping exercise anymore. Sometimes they affect our ability to gather the data correctly, but the radar sequence goes on. So on Monday evening at about 6 o'clock Pacific time, the attitude control computer went somewhere else, decided it was going to do something else for a few minutes. By the time it got back into control, we were about 5 degrees off of our proper orientation with respect to the Earth, and so we were not collecting good radar data, although, as I said, we were still collecting radar data. By about 8 o'clock, we had recontacted the spacecraft at 1200 bits per second, and by later in the evening, we had begun to send attitude updates to try to get it back in the mode where it can control its own orientation. It was through most of the night and actually into the next morning before we had good quality or up to specification quality radar imaging data. We lost a total of about 4 orbits, maybe 4.5, depending on how much we can compensate for the problems when we get the data on the ground. But we recovered and had the spacecraft back in nominal situation in about 13 hours, which is not quite a record. We did a little bit better than that last time, but still considered to be very good. Some of our spacecraft engineers said that to hurry it much faster than the amount of time that it's been taking us is actually probably not a smart idea. So we can count on these walkabouts continuing to happen, although their frequency does seem to have gone down since we got into orbit. And we can count on our ground controllers and our spacecraft software, which we have changed a little bit, to give us very short recovery times and a minimal loss of data from the planet. Speaking of the planet, I didn't mention that we're now up to 62% of the data, counting on getting to 85% by May 15th, leaving us only a fairly small job in Cycle 2 of filling in the gaps. Well, today, in the second segment of our program, we want to tell you a little bit about how someone who's doing research on this radar data of Venus goes about doing their job. So we've asked Annette de Chiron to come back. She was with us about a month or so ago, to tell us how she looks at pictures rather than more about what she looks at. Hi, Annette.
Hi.
Welcome back.
Thank you.
How is radar different from a camera? I think that's probably the most common question anybody asks.
Radar is different because it measures a number of things. It measures the surface slope as measured by the radar. If you're facing towards the radar, I have some diagrams here.
Okay.
Okay, so this is the Magellan, the schematic diagram of the Magellan. So as a mapper like myself, what we think about first is the incidence angle. Okay, so this is a radar beam coming towards a planetary surface. And the incidence angle is dependent for Magellan on where on the planet you are. At higher latitudes, you have a smaller incidence angle. Okay, and you measure a lot of the slope effect. So if there's a surface sloping back towards the radar, it'll appear bright. As you get more towards the equatorial latitudes, you have a higher incidence angle, which tends to show roughness on the scale of the wavelength of the radar, which is 5 inches.
Okay, so if I go down around the equator, then I'm looking more at how wrinkled.
Yeah, wrinkled or rough. If you have cobbles versus sand, that type of thing is what is going to is the actual image you're going to see. So when people map, we have to take into account where we are on the surface and take that into the interpretation.
Okay, let me just try again. If here's a piece of the planet, okay,
right.
When I'm up toward the poles, I can't tell so much about how rough this paper is, but I can tell whether it's like this or like this.
Right, the angle towards the radar, and we know, because we know where the spacecraft is, we always know that it's coming down from the left, so we'll know relative to that what the slope is.
Okay, then if I get toward the equator, I can't tell quite as much about how much like this it is, but I can tell whether it's like this piece of paper or whether it's
right.
like, well, that didn't work so well, or whether it's like that.
Right.
Whether it's all wrinkled up.
Yeah, and the rougher will be the brighter return. Okay, and I'll show you an example of that.
Okay, great.
Okay. So this is the first diagram.
Okay.
So now we're going to start at a high northern latitude. This is about 77 degrees north.
Okay.
And this is a high slope effect. So you could imagine if you were looking from a plane on the Earth, and there was a sun angle that was coming in from the left, okay, you can see this is bright terrain, which is surfaces that are associated probably with mountainous areas that are reflecting back towards the radar. Okay, and you see this little feature. It looks like a river channel almost. There's no water on Venus, so it's actually just a lava channel on Venus.
Okay.
But this is the far wall, which is reflecting back towards the radar. It is bright. Okay, and you follow that around, and on this side, it's a dark return because we're now not facing towards the radar anymore.
Okay, so this is almost like a mirror.
Yeah.
That the edge of the, well, I guess you've got a graphic here.
Yeah, I have a graphic which will show you. So here we go. This is what a geologist would map. Okay, so here is our channel, and these little tick marks which go in towards the channel, they represent a slope. The tick mark always faces down slope.
Okay, so you can tell that this guy is not a bump,
right?
But it's instead of
the map symbols
surface.
show that this is a slope that's facing this way.
Okay.
Okay, this red line represents a cross-section, which we have down below here. So imagine if you cut a slice through Venus and we're looking, you would see at this red that this would be the channel. Okay, so this is this side, and this is that side. So here comes the radar beam. At this latitude, 77 degrees, the incidence angle is 21 degrees. Here it comes down. It's a 21-degree angle, and on this wall there's going to be a bright return, represented here, and on this wall, because the wall is actually paralleling the radar, the return is going to go away from the spacecraft, and it's going to look dark.
Okay, so let's see. If we go back to our picture then, maybe we can show that. Okay, so I'll go in real close here.
Okay, good.
Now, you can tell that that's a valley,
right,
because this side's bright.
This is bright, this is dark, this is dark, and this is bright.
Sure. If it were a mountain, it would look exactly the opposite.
Yep.
Okay. And speaking of
and actually, if we want to just zoom in and see the tick marks I was talking about that show the slope, that's what they look like. This is what I do.
Okay, so that's your way of sort of indicating that you've looked at the shadows, not the shadows, but the bright parts,
right,
and you can now tell what's going on.
Yep.
Very good. Okay.
Okay, the next example is these are called pancake domes, is what we've called them because of their shape. Okay, they're these circular features. They're located about 30 degrees south latitude, and they have an incidence angle of 32 degrees, which takes a sort of equal roughness and slope.
Okay.
So
this is midway between the two cases you were talking about. Okay.
So on this side is very bright, okay, and this side is darker. Oops, I'm not, here we go. This is the bright side, and this is the relatively dark side. The radar is coming in. this is reflecting back towards the radar, and this is not.
Okay.
And also there's some roughness associated with the top of the dome, and you can see that as little bright reflections.
Okay.
Okay?
Okay.
So here's our geologic map again. The tick marks are going away from the dome. They're circular in shape, and here are the tick marks going away.
Mm-hmm.
This is a cross section. You can see that's why we call it a pancake. It's a steep side and very low in the middle. Here comes the radar beam down at 32 degrees, reflecting off of this sharp edge, and that's why it's so bright.
Okay.
And this, you can see the scale is about 12 miles.
Now, at the same time, this area in the middle is getting some return from just the rough surface.
Right.
Okay. Very good. Boy, those are weird shaped things.
Yeah.
Okay.
Okay.
Case number 3.
Case number 3. This is impact crater called Aurelia. It's located. The incidence angle here is 44 degrees, and you can see the variations in roughness here. When you have an impact, you very often get a bright return, very hummocky. This is the ejecta blanket. Here's a central peak, bright on the side that's towards the radar. Here's the slope that's bright on the side towards the radar. So you see the hummocky ejecta blanket, but then you also see a volcanic flow down here, if we can move that up, which is halfway. It's not as smooth as the dark plains, and it's not as rough as the ejecta blanket. So we know that this is probably some sort of a volcanic flow, not ejecta.
Okay. Now, if we took this crater and moved it up toward the North Pole, where the radar angle was incidence angle was much steeper, then would this crater look pretty much like that river, that lava river?
You would.
It'd be real dark in the middle. It'd be real bright over here, and really bright, I guess, over on this side, right?
Yeah. So that would you would see less of the roughness and more of the slope. And we have one more.
Okay. Well, let's see here now. Is this lava flow also likely to be sticking up, so that it would, if we were looking at it at the North Pole, so that it would give us a bright side on this side?
That's likely. I mean,
Okay.
it's hard to tell from here, but that is a possibility.
Okay.
What stands out now at this area is the roughness of it.
Okay. Now, what's going on the outside here? That's all dark.
Yeah,
So that means it's all very smooth.
Yeah, there could be smoothing. Maybe when the impact happened, there could have been some scouring of the surface, maybe baking of the surface, which smoothed it out. We often see that in craters from Magellan data.
Okay. I guess I sort of derailed you here. Okay.
Oh, it's okay.
Show me.
So this is, once again, the line going across. Oh, another interesting thing is this geologic symbol that has to do with impact craters. You have the double line instead of the single line, but it also shows the slope down towards the inside of the crater. Here's the central peak. Here's a cross section showing the different edges in the central peak, and here's a radar beam. And this is how we map flows.
Okay. Now, when yesterday at the science briefing, Eric DeYoung showed, or Steve Saunders showed Eric DeYoung's movie where you could actually see these as if you were flying over this.
Right.
He knows what these slopes are by the same mechanism, right?
Yeah, he uses
Okay.
radar clinometry, which
So if it's sloped, it's bright.
Right.
Same thing that happens at the North Poles.
right.
When he gets down to these equatorial places where this incidence angle is greater, that must get harder to do then.
Yes, it's more of a geometrical problem. You need more than one image. You need to see several to make sure that you're looking at the right thing. It's more complicated, but using computers you can do it.
Great.
So.
Great. Okay, well, thanks a lot, Annette. That's great. It's a very interesting thing. It's fascinating to me, and I hope to you, to begin to sort of look into the minds of the people that are actually doing this work, and to see not only the results, that is, that this is a crater, and this is a mountain, and this is a lava flow, but begin to get a feeling for how they do those things and to how they understand them. Next week, we will, well, first of all, let me tell you that we are back into normal mapping now. We are back into our attitude specification, and we're back collecting normal data. Next week, we'll talk some more about science and about how the interpretation is going on of these data. We have now a large group of people who are concentrating on the mosaics, and I think next week we're going to tell you more about how the mosaics are formed and what mosaics we currently have. Okay? We'll see you next week.